Improvements to Pierce County's Lahar warning system are in the works to help warn people earlier in the event of a volcanic eruption at Mount Rainier.
Well, it was definitely the talk of social media on Wednesday morning. Some panic over Mount Rainier.
Snow-capped, majestic, and a symbol of the Pacific Northwest, Mount Rainier is one of America's most iconic volcanoes. Towering over 14,400 feet, it draws hikers, scientists, and tourists alike with its rugged beauty and glacial dominance. But recently, the peace beneath the peak has been broken. In April 2025, geologists began detecting a swarm of unusual earthquakes beneath Mount Rainier. These weren't your standard background tremors. They were deeper, more frequent, and some displayed unique waveforms that hinted at something stirring far beneath the mountain's icy slopes. Are these signals of magma movement, hydrothermal changes, or something we haven't seen before? In this video, we'll explore what scientists are seeing under Mount Rainier, what makes this recent earthquake activity different, and what it could mean for the volcano, nearby communities, and the future of volcanic monitoring.
Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
The threat includes Mount Rainier, which scientists continually monitor for activity. New at 6.
Mount Rainier, the sleeping giant of the Cascades. Mount Rainier is the tallest volcano in the Cascade Range and one of the most dangerous volcanoes in North America. Classified as a stratovolcano, it has steep flanks built up from alternating layers of andesitic lava flows, explosive ashfall deposits, and pyroclastic surges. Its towering profile is not just scenic. It's built on thousands of years of dynamic and sometimes violent geological history. Rainier's upper slopes are sculpted by more than 25 major glaciers, the largest glacial system in the contiguous United States, which contribute to its beauty and risk. This massive mountain hasn't experienced a major magmatic eruption in over a millennium, but dormancy is not the same as inactivity. Even in repose, Rainier remains seismically and thermally active. Its summit and upper flanks are lined with fumaroles, vents that constantly emit steam and volcanic gases. These gases indicate that magma is still present at depth and that the volcano's hydrothermal system remains vigorous. Scientists consider it an active volcano because it continues to deform, degas, and shake. To ensure public safety, Mount Rainier is monitored around the clock by the U.S. Geological Survey, USGS, and the Pacific Northwest Seismic Network, PNSN. These agencies have deployed a sophisticated array of instruments, including broadband seismometers, continuous GPS stations, gas analyzers, and tilt meters. Together, these tools allow experts to detect even subtle changes in the volcano's behavior, whether it's ground swelling, chemical shifts in gas emissions, or changes in tremor patterns. The primary hazard Rainier presents isn't lava or ashfall, though both are possible. The greatest danger is lahars, volcanic mud flows triggered when eruptive heat or structural collapse causes rapid glacier melt. These lahars can sweep down the mountain's river valleys like a slurry of concrete, destroying everything in their path. Historic lahars have carved out deep channels and filled lowland areas with meters of debris. Because of the immense ice volume on Rainier, even a small eruption or non-eruptive event like a flank collapse could mobilize enough material to create catastrophic flooding. Over 3 million people live within the extended hazard zone of Mount Rainier, especially along river systems like the Puyallup, Nisqually, and Carbon. Communities such as Orting, Puyallup, Sumner, and even parts of Tacoma could be impacted by lahars with little warning. This proximity to population centers makes Rainier one of the most dangerous volcanoes in the country, not because it erupts often, but because the potential impacts of even a moderate event would be widespread and devastating. It is this combination of massive ice cover, steep topography, active volcanic plumbing, and dense downstream population that places Rainier high on the USGS's list of high-threat volcanoes. The mountain is majestic, but it also holds the power to change landscapes, communities, and lives in a single day. That's why the current unusual seismic activity has caught scientists' attention and is being studied with heightened urgency.
Media may have erupted earlier this morning, but Mount Rainier did not. The final word from the national park? It was a cloud that caused the volcano to look like it was venting earlier this morning.
The earthquakes begin. What scientists detected. In mid-April 2025, a small cluster of seismic events was recorded near Mount Rainier's western flank, about 5 to 10 kilometers below the surface. At first, these appeared similar to typical background activity seen beneath the volcano. But within days, the frequency increased and the pattern became stranger, triggering widespread attention from the geophysical community. Some of the earthquakes were deeper than usual, between 10 and 14 kilometers, and clustered in tight swarms that persisted for multiple days. The shifting epicenters moved progressively in a north-northwest direction, suggesting either fault migration or fluid transport within an inclined structural zone. Others occurred at intermediate depths, 5 to 8 kilometers, and exhibited low-frequency, long-period waveforms. These types of quakes often indicate the presence or movement of fluids, like magma, superheated water, or volcanic gases. Their depth profile, just above the brittle ductile transition, makes them especially relevant for understanding how heat and pressure are being redistributed inside the volcano. One of the most notable features was the appearance of earthquake multiplets. These are small tremors that repeat with almost identical seismic signatures, suggesting they are caused by the same source event, often interpreted as pulsing fluids or a repeating fracture along a constrained fault. In some instances, the multiplets came in rhythmic bursts, dozens of nearly identical quakes spaced minutes apart, indicating a non-random process was triggering their recurrence. To enhance detection, machine learning algorithms were applied to real-time data streams. This analysis revealed additional low-amplitude multiplets that traditional manual methods might have missed. The results pointed to multiple localized pressure centers interacting within a confined crustal volume, potentially outlining a narrow conduit system or magma sill. To geologists, this combination of deep swarms, low-frequency quakes, rhythmic multiplets, and subtle migration patterns points to something more dynamic than just tectonic stress. It suggests that Mount Rainier's deep plumbing system is adjusting, possibly accommodating a new influx of magma or experiencing structural rearrangements in response to stress redistribution. Something is moving, and the mountain may be preparing to speak more loudly. What makes these quakes unusual? Earthquakes under Mount Rainier are nothing new. On average, about 1 to 2 small tremors occur each week. Most are shallow, less than 5 kilometers deep, and many are linked to glacial processes like ice cracking or rock shifting under pressure. These ice quakes tend to occur seasonally, particularly during periods of snowmelt or rapid glacial motion, and they rarely form patterns or clusters that draw scientific concern. What makes the April 2025 swarm unusual is its depth, duration, and seismic signature. These are not surface processes. These are occurring deep in the Earth's crust, near where magma chambers and hydrothermal reservoirs reside. The focal depths, between 8 and 14 kilometers, place the origin of these tremors well beneath the glacier zone, within the brittle crust where magma intrusion and fluid migration typically occur. This depth alone makes them seismically significant, as it rules out the majority of non-magmatic surface mechanisms. The multiplet pattern also raises eyebrows. In typical tectonic events, earthquakes occur in random patterns as stress accumulates and releases along faults. Multiplets, however, suggest a stable, repeating trigger, something like fluid injection, migration, or oscillation. This points to the possible movement of magma or hydrothermal fluid through small fractures in the crust. In some cases, Multiplets are also associated with resonance phenomena, where a fluid-filled cavity vibrates under pressure, releasing repetitive pulses of energy. At Rainier, this may indicate a partially pressurized system that is releasing tension in regular, discrete intervals. The sheer number of events is also notable. Between April 12th and May 1st, more than 120 quakes were recorded in the affected zone. That's nearly 10 times the average for a typical month. Their waveforms have been carefully cataloged and show high similarity in frequency content, duration, and amplitude. Though most were too small to be felt, their consistency and depth profile make them geophysically significant. Some tremors displayed harmonic overtone, another potential marker of fluid resonance within the crust. The recurrence interval and waveform shape suggest a non-random, possibly pulsatile behavior, further strengthening the case for active subsurface fluid dynamics. In addition, these quakes have shown a subtle lateral migration pattern, shifting slightly westward and upward over time. This type of migration may reflect the movement of pressure or fluid through a fractured medium, potentially outlining a pathway for ascending magmatic or hydrothermal material. For volcanologists, such migration is a key detail in interpreting whether a system is pressurizing and evolving toward an unstable state, or simply self-regulating through slow, episodic discharge. Either scenario warrants close observation. What could be causing this? So, what's driving these unusual earthquakes beneath Mount Rainier? There are three leading hypotheses. Magma recharge. One possibility is that magma is rising from deeper in the mantle and slowly filling a mid-crustal reservoir. As magma intrudes into surrounding rock, it can cause earthquakes by creating pressure, fracturing rock, and displacing fluids. This kind of slow recharge process may not lead directly to eruption, but could signal that the system is entering a new phase of activity. Magma intrusions can also change the chemistry of the hydrothermal system, possibly triggering secondary effects. Hydrothermal system disturbance. Rainier has an active hydrothermal system beneath its summit and flanks. Superheated water and gases circulate through fractures and porous rock. Changes in pressure, heat, or permeability in this system can trigger swarms of small quakes, especially at depths of 5 to 10 kilometers. If new pathways open or old ones collapse, pressure redistribution could produce earthquake multiplets and low-frequency tremor. Hydrothermal explosions, while rare, have occurred in similar systems when steam pressure becomes trapped. Tectonic stress transfer. The regional stress field in the Cascades is complex. The earthquakes could reflect changes in how tectonic stress is being distributed, possibly triggered by deeper plate movements or small adjustments in fault zones beneath the mountain. If strain is shifting laterally from adjacent volcanic centers or subduction interface creep zones, Rainier's internal structure might be responding. How scientists are responding. In response to the uptick in seismic activity, the USGS and PNSN have increased monitoring efforts around Mount Rainier. Several new portable seismometers have been deployed near the western flank to improve location accuracy and waveform analysis. These instruments complement the permanent seismic stations already in place, offering finer resolution and redundancy across sensitive zones. The increased density of monitoring will help researchers distinguish between tectonic, hydrothermal, and magmatic quakes, and better identify swarms, tremor bursts, and multiplets in near real time. GPS stations are being scrutinized for signs of surface deformation, any indication that magma or fluids are physically uplifting or tilting the ground. Analysts are reviewing both horizontal and vertical components of GPS motion to detect subtle inflation patterns. In addition to surface tilt, they're also watching for any signs of accelerating displacement or strain accumulation across fault segments. So far, no major changes have been detected, but the data is being updated daily and analyzed alongside satellite-based radar interferometry to verify consistency. Thermal and infrared imagery is being collected from satellites and aerial drones. These tools allow researchers to identify localized hotspots and small changes in ground temperature that could reflect increased hydrothermal flow, lava dome heating, or incipient fumarolic activity. Drone-mounted FLIR cameras provide high-resolution surface scans that can detect variations of less than 1 degree Celsius across snow, rock, and vent areas. Gas sensors near summit vents are also under review. If rising magma is approaching shallower levels, it may release increased amounts of carbon dioxide, CO2, and sulfur dioxide, SO2. These gases typically escape from magma as it depressurizes during ascent. Scientists are watching not just for absolute increases in emission, but for shifts in the CO2/SO2 ratio, a diagnostic indicator of gas saturation and magma depth. So far, emission levels remain within normal ranges, but close tracking is essential. All these efforts are part of a tiered volcano monitoring strategy aimed at catching early warning signs before surface activity begins. This strategy involves real-time telemetry, cross-reference datasets, and collaboration with emergency planners. The goal is simple: to detect even the smallest changes in Mount Rainier's behavior before they become major events, and to ensure local communities have the lead time they need to act. Why this matters: risks to communities. Mount Rainier's beauty belies its danger. A minor eruption or even a landslide could produce lahars, volcanic mud flows capable of reaching the Puget Sound lowlands in under 2 hours. These lahars are among the most dangerous volcanic hazards, not because of fire and ash, but because of speed and scale. These flows follow river valleys like the Puyallup, Nisqually, and Carbon, where tens of thousands of people live. The lahar pathways have been mapped using geologic records, LiDAR scans, and hydrological modeling, and the results are sobering. Entire communities, including schools, hospitals, nursing homes, and highways, lie within these mapped lahar zones. The valley floors are flat, low-lying, and offer little resistance to fast-moving debris flows. The time between detection and arrival could be less than 45 minutes in some cases. If magma is slowly building up beneath Rainier, even without an eruption, it could destabilize portions of the mountain. A flank collapse, for example, could release millions of tons of glacial ice and rock, generating a massive debris flow without any lava. Historical examples like the Electron mud flow and Osceola mud flow show that non-eruptive events can still produce lahar deposits tens of meters thick and travel dozens of miles. These events likely reshaped landscapes and river channels permanently. What we've learned from past unrest. This isn't the first time Mount Rainier has experienced seismic unrest. In 2009 and again in 2011, smaller earthquake swarms were recorded beneath the summit area, largely characterized by shallow, high-frequency events. In those earlier cases, the activity eventually subsided without incident, and no other geophysical changes were observed. The swarms were interpreted as minor adjustments within the shallow hydrothermal system or glacial stress events, and they did not appear to involve deeper magmatic processes. But the current swarm, first observed in 2025, is deeper, more structured, and more persistent than previous episodes. Seismologists have noted that the spatial clustering, waveform similarity, and temporal pacing of the recent quakes are distinctly different from those earlier swarms. It also coincides with a regional pattern of increased seismicity across the Cascades, including renewed unrest at Mount St. Helens and subtle tremor episodes beneath Glacier Peak. This broader activity may reflect changes in regional stress distribution along the Cascadia subduction interface or mantle flow patterns beneath the arc. Should we be worried? Right now, the official alert level at Mount Rainier remains normal. There is no current evidence of magma rising to shallow levels, no deformation of the surface, and no changes in gas output that would indicate imminent eruption. However, that doesn't mean this activity should be ignored. These unusual earthquakes are a reminder that Rainier is active and capable of change. Even without eruption, it can generate hazards that affect thousands. Preparedness remains key. Communities near Mount Rainier should stay informed, review evacuation routes, and support local emergency planning efforts. Meanwhile, scientists will keep listening because sometimes it's the small quakes that signal big changes to come. Drop your thoughts and questions in the comments below. Don't forget to like, subscribe, and share this video with anyone living in or curious about the Pacific Northwest. Until next time, stay curious and stay ready, because even sleeping giants have a way of waking up.